Okay, so in this example 9, we have a function f of x equal to x squared minus 3x plus 2 divided by x plus 1, and it's asking us to graph it, sketch the graph, so, just give us an idea what the graph looks like. So I started off by finding the domain, and, that involves finding the denominator and setting it equal to 0, and when you set it equal to 0, you end up with the number -1, which is bad, and so that means all the other numbers are good, and that's how I did step 1. Step 2 said find the x and y intercepts, and in order to do that, I took my x intercept. To find the x intercept, let's say, I took the function and I made it equal to 0, and that involves basically saying something like I want the numerator to be equal to 0, and then you factor it and you get the numbers 1 and 2. And for the y-intercept, you let x be equal to 0, and that's pretty straightforward at that point. So once you let x be 0, every x that you have in the problem becomes 0, and you're basically finished. 2 over 1, which is 2. So at this point, we're looking for the inner asymptotes, and so the asymptotes are -1 from step 1 because it was a bad number and doesn't make the numerator equal to 0 either. There are no horizontal asymptotes because the degree on the numerator is more than the degree on the denominator, so that means the limit does not exist. And finally, for slant asymptotes, we will have one, and I'm about to find it using the long division. So pause the video and see if you can get the answer like I just did. So after I do the long division, I get x minus 4 and the remainder of 2, so the slant asymptote has the equation y equal to x minus 4. Okay, is the slant asymptote. Okay, so hopefully you get the same thing. If not, let me know and I'll try to answer the question. So I'm gonna move on next to the x, to the maximum and minimum, and the increasing and decreasing intervals, and the concavity. So I'm gonna fill in the blanks and show you that. So pause the video and see if you can do it for yourself. But here's the answer. Okay, so the first derivative test is basically finished. First, I need to make sure that the derivative is equal to 0. In order to do that, I grab the numerator and I set it equal to 0, and unfortunately this problem does not factor very nicely, and in order to solve it I have to use the quadratic formula. In case you forgot the quadratic formula, basically it says the following. It says if you have ax squared plus bx plus c equal to 0 and you want to solve it and it doesn't factor, you can use the formula -b plus or minus square root of b squared minus 4ac all divided by 2a. So I'll leave the formula here so that you can see it, but that's basically what the formula looks like. And once you have the formula and you simplify the expression and everything, you get the numbers -1 plus or minus radical 6. So those are the first two critical numbers, and we get from the denominator, setting the denominator equal to 0, we get that the derivative has another critical number. In this case, the derivative has a critical number of -1. And again, that's already known because it was already a bad value from the start of the problem. So it was a bad value, which means that it's not going to be a maximum or a minimum ever. And testing some random numbers, I get plus minus minus plus, which means the function was up and then down and then up. So that creates a maximum and a minimum. So that's the end of that one. Let's talk about the concavity next. So go ahead and start and pause the video and see if you can get the answer that I will get. So there's the second derivative test, and again, in order to find out what makes the second derivative equal to 0, I grab the numerator and I set it equal to 0, but that's not possible. The 12 can never be equal to 0 itself. And to find out what makes the second derivative undefined, and I take the denominator and I set it equal to 0, and I get that the number should be -1, which is one of the bad numbers from step number 1. So again, bad means I should put a little circle there instead of a tick to remind me not to call it inflection point or whatever. And for this problem, the second derivative would look like this. Negative at first, then positive afterwards, which means the function is concave down at first, then concave up afterwards. And so, unfortunately for -1, it's not going to be an inflection point because it was a bad value. So let me record that. Okay, now that we've done step 1, 2, 3, 4, 5, let's go ahead and put everything together. So I'm going to start by graphing the x and y intercepts along with the asymptotes of this graph. So in the meantime, you should be doing the same thing too, please. Okay, so this is what the intercepts look like. So there were 2 x-intercepts from the beginning of the problem. So there they are, and there was 1 y-intercept, so there it is. I put the the vertical asymptote x equal to -1 and the slant asymptote y equal to x minus 4 by just graphing a few points on the line. And so basically when x is 0, I got -4, when x is 1, I got -3, when x is 2, I got -2 by plugging the numbers into this thing basically. And at this point, we're going to connect the graph, and keep in mind that the function was increasing before -1, and at the same time it was concave down, so it kind of looks pretty much like this. There's a maximum at the point -1, negative radical 6, which roughly translates to -1, negative radical 6 roughly translates to -3.4. So I know that the maximum is happening there, but the graph is going to be kind of like down here. So it's going to sort of kind of go up like this and then come back down. It's a very squish graph because of my scales on this particular page, but you know, you can take a better look at it in your calculator. So next we have another maximum at the point -1 plus the radical 6, which is roughly speaking 1.4. So this is the point where x would be -1 plus radical 6, which is a minimum in this problem. And so it's gonna kind of like dip right below the x-axis a little bit, and it's gonna come back up, and basically it begins at the asymptote, it's gonna come down all the way to the minimum, come back up, and continue along in the direction of the green line. So eventually it's gonna be connecting with the green line. They're gonna get closer and closer to one another if we keep extending over and over again. So, you know, try to make a graph that's kind of nice and smooth, that passes through those 3 points and kind of go off in that direction of the green line. And that's gonna be the end of the graph for now. I would recommend putting this in your calculator. When you type it in your calculator, just remember to type in x squared minus 3x plus 2 divided by, and use parentheses for the denominator, x plus 1, close the parentheses. So put this in y1 along with the window where the x minimum is, let's say -20, the x max +20, and y minimum -20, y max +20 again, and you'll see a better idea of what the graph looks like. So I found that these dimensions would give a pretty nice graph, and if you really want to see the horizontal asymptote, or rather, sorry, the slanted asymptote, you could go into y2 and put in the equation x minus 4, and that would give you this guy, and it will show you the asymptotes and how the function and the asymptotes are getting closer to one another. So that's it for now. I'll see you in the next video.